Same for Poisson equation. This is the law, right? Maybe you don't know exactly what it is, but you remember we have this. And if you can memorize this form, it is even better, right? So let's keep practicing this until the end of this semester, okay? So let's talk about the scaling. In the history of transistor, at the old time, right? You can see the transistor by your bare eye. And they have this integrated circuit. But then the Moore's law, Gordon Moore from Intel, after a few years of experience with Intel's chip, you see that, wow, we can keep making the transistor smaller and smaller. And he said that we actually can put more transistor in the same area. At the beginning, he said, double the number of transistor per unit area. Why this is a big deal? This is because you put more transistor, it means that for the same cost, for the same dollar that you put in, you buy the chip, you get double the function. And that is a big deal, right? Now it has been double for so many times. Later, he revised it to be double every 1.5 years. But up to now, the first one is like maybe 1,000 transistor or something, a few thousand for 4004. Now Intel's are talking about 2 billion. That is a lot, right? But how do we scale them, right? If you load device physics, you find that it is impossible to scale it if you don't scale it in the right way. So Dennard came up with a scaling law, right? So this is something I want you to appreciate, because you understand this law, you understand a lot of physics. So he said that I'm going to optimize the transistor, okay? I'm going to optimize something called constant field scaling, meaning that I try to make the electric field constant when I scale it. Like I do make the transistor smaller, but I make the electric field constant. So can you tell me, what is the expression for electric field? How is it related to the dimension and the voltage? Electric field equal to potential divided by what?
Distance.
Thank you, distance, right? So if I have an electric potential here, let's say this is 1 volt, this is 0 volt, and if this is 1 meter, then the electric field is just equal to 1, which volt per meter, okay? So now he said that I want to scale it, right? Scale it, of course, you need to reduce the thickness, T, right? This is T. Then it means, how should I scale the voltage? I should scale it by the same amount, right? So this is what he proposed. All linear dimension scale by kappa, right? For example, if kappa equals to 0.7, then when you scale 1 micron, after scaling, it becomes what? 0.7 micron. You make it smaller. But remember, you don't only scale the dielectric. Look at this. We don't only scale the gate length. We scale the depth also. Do you see that? So you need to make them scale at the same time, right? You're just doing miniaturization, right? You see all those real airplane, and then make a Lego model. They say, oh, they are 1 to 1,000, 1 to 1,000 ratio. They scale everything, right? The window need to be scaled also. You cannot just scale the length and keep the tall the same, right? Now, and then he also say that in this time, the substrate doping also need to be scaled by copper. So for example, when this is reduced, the dimension is reduced by 5. Do you see that? For example, this one divided by 5, so copper equal to 1/5, right? What happened to doping? It is multiplied by copper. Not multiply, increased by copper. So here is a little bit sorry, this the copper here, right? If you say reduced by copper, this copper is actually 5. This is divided by 5, okay? And this is multiplied by 5 to be more accurate, right? Because he said dimension reduced by copper, but substrate increased by copper. Here the copper is 5. Is that okay? So that's how you do the scaling. But why we need to do that for substrate? Let's do it one by one, okay? The first thing is, do you remember what is the current of a transistor? Anyone? Just a typical one. Saturation current. Anyone remember?
If it's, no, that's a diode. Never mind.
Well, it's half mu and Cox.
W of half?
Yeah, W over L.
W over L?
VGS minus VTH squared.
Very, very good, right? If you cannot memorize, no problem, because if you don't deal with it every day, right? But now in this class, you also don't have to memorize, but you need to know how each term is affecting it, right? Mu is the mobility. Higher mobility, higher current. Oxide capacitance, higher current. We are going to discuss this. Wider transistor, longer transistor, what is W on L? Let's draw the transistor. Transistor is like this. This is the gate. We have a so-called spacer. And then we have source, we have drain, right? We're talking about the current going in I. My internet is a little bit broken. Let me say again. This is the cross section of the transistor, right? And this is the gate. And if you try to look in 3D, it is something like this. This is L, the length, and this is the width. And this is just a resistor. So longer gate length, smaller current, right? Smaller gate width, smaller current. And VGS is just the gate voltage. Of course, you apply higher gate voltage, you have more current. So, okay? Now, then what I want to show you first is that it says substrate doping increased by copper. Why we want to do that? The goal is that to reduce depletion width I have some problem with my computer. You can still hear me, right? Oh, hold on. Usually this means there's something wrong with my, and can you see my screen?
Yes.
Okay, now I try to write depletion. Can you see that I'm writing?
Yeah.
Okay, thank you. Now, the reason we want to scale the substrate is to reduce the depletion width. Remember what? Oh. Yeah, the whole thing screw up. Remember Dennard say what? He said that I want to scale all linear dimension. All linear. This includes the depletion width. What we are drawing here is the depletion width. This is the W. Okay, and let me call it WD, right? Just so that you won't get confused later. WD, right? So our goal is to reduce the depletion with WD. Okay, now let's go back to the depletion width equation, WD, right? Let me give it to you. But now I don't need to say, I just give you, say, it is proportional to the voltage and inversely proportional to the doping. So what did we say about the voltage when we do the scaling? What do we say for Dennard? Dennard. Reduced by copper, right? So it becomes becomes V divided by copper. Voltage is the voltage you apply to your transistor. It was 5 volts, becomes 3.3 volts, becomes 1 volt. Okay? And then how about NA? he said that we should increase it by copper. So what is this? It becomes V divided by Na times 1 over copper, right? So it means the depletion width is reduced by copper. Do you see the rationale? Is that clear? So the whole scaling history is that when we try to make the dimension smaller, we also need to increase the substrate doping, which is not good. Eventually, we find that it is not good. It has a lot of scattering effect. It reduces the electron mobility. It increases the band-to-band tunneling, the leakage current. But in order to make the transistor working, we need to keep increasing the substrate doping. Is that okay? Any questions? Now, it also tells us that the current is going to reduce by copper. Is that right? I just asked you what's the current, right? So I did not write in the correct sequence. I copy here. So can you tell me what happened to the mobility when you make it smaller? Basically the same. But what happened to the capacitance when I make all linear dimension smaller, not smaller, by copper? What happened to the capacitance? Do you remember? Capacitance here refers to the gate capacitance. Refer to this. This is C-ox, and this is T-ox. So when I will say we try to make all linear dimensions smaller, what happened to the capacitance? Is increase or decrease? First, is the T-ox increase or decrease based on Dennard scaling? Let's look at the equation again. First of all, of course, the T is going to decrease, right? Because we try to make the linear dimension smaller, right? And how about for capacitance? It's going to be larger or smaller? Anyone please help me?
Get larger.
Larger, because when you make the thickness smaller, your capacitance increase. Why I keep doing this? Because this is the very important concept. That's whole scaling. Why you do FinFET, why you have new dielectric is going to happen later. So this is very important. This one, right? You reduce it by copper, the capacitance is going to increase by copper. Okay, it's going to increase it. Okay. How about for W? What happened to W when you, for the linear dimension? Is it going to increase or reduce by copper? Based on the rule here, what does it say? All linear dimension reduced by copper. It's going to be reduced also, right? Because you want to make the transistor smaller. You also make the width smaller. Is that okay? How about the length? You also make it smaller. Okay. How about the voltage? What happened to the voltage? Please memorize this. All linear dimension and voltage reduced by copper. So we are going to apply a smaller voltage to it. We probably will scale the threshold voltage also, right? So these two get cancelled, right? This becomes, I should say this becomes this, right? So then, it means the current is going, what happened to the current now? This got cancelled, this increased by copper, but this decreased by copper squared, right? So currents decrease by copper. Any questions on this? So the reason, so we reduce the dimension. we reduce the voltage, and we also reduce the substrate doping, right? We increase the substrate doping. By doing so, we can keep having the linear dimension, including the depletion width, reducing at the same time. And the result is reducing the current. Why you want to reduce the current? That comes to the last 2 points. Because the power per transistor reduced by kappa square, and the delay will be reduced by kappa also. You actually make it faster. Wow, that is interesting. I don't know if you think about that. I reduce the current of the transistor, my circuit is faster. How come? And this is the number 3, right? What is the delay? How do you calculate the delay? Delay is just the time, right? And time is related to the current, the voltage, times the oxide, the capacitance, divided by the current. Basically, this is the charge, right? So you have a gate capacitance. You multiply the voltage you want to change to, right? For example, you need to charge from 0 volt to 5 volt. And then you have this current. Then how much, then this is the delay time, right? So what happened? What happened to the voltage? Can someone tell me in this scaling?
Decreased by kappa.
Thank you. Decreased by kappa. What happened to the capacitance?
Also decreased.
Now, this is some insight I want you to be able to memorize. Now you say it's decreased. Probably you are saying the oxide thickness is decreased. When oxide thickness decrease, here, what happened to the capacitance? Increase, right? When oxide thickness is decreased, capacitance increase. Okay? So this becomes this. What happened to the current? I missed something.
Decrease.
Current will decrease, yes. But sorry, I missed one important thing. The oxide I'm giving here is per unit area. Okay, this is per unit area. The capacitance I'm giving here, sorry, the capacitance I'm giving here is per unit area. Okay, so the capacitance we're going to charge, I actually should multiply this by WL. Right? If you look at this figure, this is the area, which is W times L. You use this one to drive the next stage, right? So I should multiply that by WL, right? So the voltage, yeah, decreased by kappa. The capacitance increased by kappa. Actually, I hope that you already have the sense, starting building the sense. When we scale the transistor, we make the substrate doping larger. We make the dimension smaller. We make the voltage smaller. In this process, capacitance is getting larger. Okay, we proved that already. It's getting larger. Okay, and of course, the width is going to reduce. The length is going to reduce. Area reduced by kappa square. That's the main point. For the current, it's going to decrease. Why? Because we just proved it. See that? We just proved that current decreased by kappa. Okay? Because of this, you see that the delay, right? If you try to cancel them, am I right? Yeah. You try to cancel them. This is 1 over kappa squared divided by kappa, right? Reduced by kappa. You just cancel that. So it means that if I follow Dennard scaling rule, if I reduce the transistor size by half, I can increase my clock rate by double. Any questions? Anything? Any question about this? Now let's talk about the power consumption per transistor. What is the equation for power? Voltage times current, right? So we say that the voltage is reduced by copper, currents also reduced by copper, so the power is reduced by copper square. Now you see that the point is, yeah, you put more transistor on the same chip, but the total power is still the same because you make them smaller. So the power consumption per transistor is reduced by copper square. So even it was 1 watt, 100 watts before, if I follow this scaling, I still have 100 watts, but my function increased by many times. Any questions? Now maybe you feel that this is a little bit boring, why I want to go through this, but this one actually is the background, the backdrop of the whole play, of the history. I hope that even you cannot memorize everything, you have the sense, the intuition. When people talk about transistor scaling, it's not just dimension smaller. You immediately know that gate oxide also thinner. Depletion width is also smaller. And then you know the capacitance is larger. That is what we want. And power consumption is actually similar if we can follow this Dennard scaling. And this has been doing from 1970 all the way to 1990s. Works very well. So people say that was the easy time for semiconductor. You just keep doing this scaling, and you have better products. Is that okay? Any questions? Feel free to ask. Now, so this is something I hope that you can learn from doing this hand waving calculation, right? Because being able to estimate is a very important merit for engineer. Okay, the rest, let TCAD do it, let computer do it. You want to have an insight, okay? Now, so we talk about Moore's law, right? For Moore's law, we already say that it increased the transistor in a single die. So how do they do that? Remember, they, besides miniaturization, make it smaller, it actually also try to increase the die size. If the die is larger, then I can put more transistor. Also, design cavernous and U, right? Do some new circuits so that you have more function for the same number of the transistor and increase the U of your production. Do something so that more dies are working. When you fabricate 100 die, probably only 95 are working if you are a very good semiconductor firm. At the beginning, when you ramp up the new technology, it can be as low as 20%, which is going to lose money. Once you reach 90%, you might earn money, right? So Moore's law is not just about transistor miniaturization. Dennard's law is about miniaturization, but not Moore's law. So let's look at this figure from 1970 all the way to 2016. If you look at the transistor per die, it does go up like this. So people say Moore's law is dead. It depends on the definition. But we try not to say that because that's our job. But the main reason is that Moore's law is talking about the function, number of transistor per die. But who care about how many transistor is in the die? You care about the number just because it gives you more function. If I don't need to increase the number, I can increase the function. It is still Moore's law. So this is the mentality we need to have. And then because of that, you realize that nowadays it's not about putting more transistor there. It's about more optimization, including this design cavernous, which he's mentioned in 1975. And nowadays, that is exactly what we are doing for the new transistors. Okay? Any questions? So this is an interview. I just grabbed it from a video, YouTube or something. I forgot, right? Mark Bond is a very scientist or fellow in Intel, and he gave Intel about how the is scale, right? So just like what we said, this is a very easy error. Dennard scaling error. We just make it smaller, smaller, then you have a higher frequency. But the point nowadays is that we reach that limit. First, it's very difficult to make it smaller. But the biggest problem is not that we cannot make it smaller. It's that you make it smaller, it doesn't work. And you make it smaller, you consume too much power. And this is what Gagini, in this paper I put in the canvas, talk about. Nowadays, we cannot just improve the transistor. We need to make efficient technologies, okay? And then how are we going to solve it? A lot of content is about this, right? And then in the future, it's about scaling and heterogeneous integration, right? As I said, while you cannot put more transistor in a die, can you stack more die in the same package? Then isn't that is also another kind of Moore's law? Because what Moore's law about is functionality. Please remember this, the function of the chip that you can deliver is more important than the number of transistors it has. Who cares about how many transistors it has? We only care what it can do, okay? So, but we will start from here. For the rest of the semester, start from this power constraint, and then we will go to heterogeneous and also new technology. So what are the problem of this power? If you look at the transistor again, right? Stop me anytime if you have questions. And if it is not clear, because my internet sometimes has problem. Do you remember when we are scaling? We say that, so this is the gate. We say that the gate oxide keep reducing. What happens if you make an insulator very, very, very thin? Can someone tell me? Is it still a good insulator?
No, there will be tunneling.
Thank you. Good point. Right? When it is very small, when you go to 1 nanometer, then tunneling is very big. What is tunneling? It's a quantum mechanical phenomenon. So when it is fake for insulator, right? Electron cannot go through. But when it is very thin, electron is a wave. Wave can penetrate if you solve the Schrödinger equation. Then you have tunneling. So electron can just jump into it. And it is at the stage like this. If you turn off all the transistors, but you still apply power, right? But you turn them off. In the past, you hope that they are all, right? Remember this line? In the past, this one, I turn it off. I hope that there's no leakage, no power consumption. But nowadays, right? Of course, we avoid it. If we did not avoid, it is like if turn off your CPU, you are consuming 100 watts or higher power by doing nothing, just because of tunneling. Because when you turn it off, this might be at 5 volts. Sorry. Let's say if NMOS, this might be at 0 volt. Let's say this is at 2 volts for drain, right? And this is 0 volt, right, for source. And this is all 0 volt. It's going to have a lot of tunneling to the drain side. And it's very leaky. Electron will just tunnel there. So this is one. The first source is tunneling. The second source is the leakage between this. This is actually N plus. Drain is N plus. This is P. Can you tell me when this is 2 volt, this is 0 volt, what kind of bias is this? Is it reverse or a forward bias? When you put positive potential to the N, is it reverse or forward?
Reverse.
Reverse, right? The way I memorize is that when it is N is negative, right? So I put positive to negative, then it is reverse. When it is reverse bias, you don't expect any current. But however, when the doping is so high, we keep increasing the doping, right? Then the reverse, this is 2. Bias PN junction is going to be very leaky. I'm not going to discuss this. This is we will discuss this later, but not here. This is so-called band-to-band tunneling. Okay. The third thing, when this transistor is off, you feel that there's no current leaking, but it is not true. The current actually can leak through here. It's very small, but it's leaking. And this is the so-called sub-threshold leakage. We're going to cover these concepts later again, but I hope you keep, like my strategy is like immersion teaching. You keep seeing this every class, then you will know that very well. Sub-threshold means what? This is below threshold voltage, correct? VGS is less than VTA. There should be no current, but no, we still have leakage. This free leakage is actually causing a big trouble to the semiconductor industry in early 2000. Of course, we solved it already. We have very powerful CPU nowadays, but we solve it by new transistor and also new architecture. Is that okay? Any questions? Okay. Now, so of course, let's go back a little bit. This is about the scaling. He said that at that time, we just keep increasing the density. There's a really old stuff, not very important now, right? And then we go to different technology node. Like this is the so-called technology node. If you heard about that, people will say, right? Oh, I am using 0.13 micron technology. I'm using 65 nanometer technology, right? And then which company now can do 5 nanometer? Which company can do what? They use this to compare. In the old time, right? In the old time, you see from one generation to another generation, for example, 0.18 to, since my cheat sheet is using 0.25, let me use 0.25, right? 0.25 to 0.18. You see that the scaling is 0.7x. What is the meaning of 0.7x in the scaling? What's the meaning of the area? If the length reduced by 0.7, then it means the area is reduced by 0.7 squared, which is 0.5. This is exactly like what Dennard is envisaging, right? We reduce by 7.7 every generation. I can put double of the transistor. Okay? And at the same time, the frequency keep going up. Power keep going up also. And eventually, we run into problem. This is 100 watt. 100 watt is still okay. If you keep extrapolate, you will have problem. Okay? Any questions? But then finally, we comes to this, what I want to talk about is the problem of the power. After 0.13 micron, then we cannot just keep scaling, okay? So there are a few things we will discuss in the future. One is that we apply some strain to the silicon to enhance its performance. Electron run faster under stress. Like us, right? We do better when we are under stress. Without scaling the device, it is faster. And later, we also introduced the so-called high K metal gate, right? What is high K? High K is talking about the kappa, the permittivity, right? So let's go back again, right? If I have, let me see, okay, capacitor. As I say, the capacitance is epsilon divided by T. So when I scale it, I keep reducing the T because I want to have a larger capacitance. What happens when I do this? When I keep reducing the T? When the thickness is smaller, what happens? We just discussed the gate oxide capacitance when it's smaller. What I'm talking about is the oxide capacitance. The insulator here becomes thinner, and thinner. I have larger capacitance. Then what happened to the, what will be the problem when the thickness is very, very small?
Leakage?
Correct. You have a tunneling, right? So we have a lot of leakage. So we were in the place that 45 nanometer, we cannot scale anymore. Then people say that find a new material. This is 45 nanometer. With large epsilon, which we call high K material. High K, there are many high K material. The most successful one is hafnium dioxide to replace silicon. It has a permittivity in the range of 25 to 39. Maybe I'm wrong. Let's say 25. Silicon is 3.9. So you see that I can get, if this is 1 nanometer, right? I just put this as 10 nanometer. What do I get? Same capacitance. Because I make it thicker, but I have a larger permittivity, then I have the same capacitance. But this is very low tunneling current because it is fake. So, okay, is my explanation clear? Right? And we keep scaling, still not enough. Eventually, in 22 nanometer, Intel introduced something called FinFET, right? We'll discuss later why. But anyway, that is the point, right? Dennard scaling is there, but Moore's law is not, because we keep being innovative, applying strings, applying new material, applying new transistor architecture. Then we keep scaling to today. And what do we go next, right? I'm going to tell you, maybe I'm not good enough to tell you, watch the ERI video I sent you. Those are the leader in this area. And yeah, okay? And where the money comes from. Any questions? Right, just an idea, right? I can tell you I'm not going to test you this, but if you don't know this and you tell people you know about transistors scaling, then they won't trust you. If you even don't know about the essence, right? What we are doing. But we will go to details for each of these points later. So what are we really scaling? So I have already told you, we scale the gate length, right? But finally, you see that it doesn't change, right? 215 nanometer, it has this gate length. I'll keep going down. But gradually, just stagnant. We don't scale the gate length anymore. Okay, why? That is because slowly at this point, the delay is no longer dominated by the capacitance, gate capacitance. Remember, let's go back to here. When we calculate the delay, we say it is voltage times C ops divided by I. C ops is the gate capacitance. But in reality, we have more capacitance. If you look at a 3D view of your transistor, yeah, you will see that this is N plus, and then you actually have some oxide here. You have opening, oxide, right? Oxide, right? And then you have this metal. This is a metal. So what capacitors do you see? Yeah, I have a capacitor. This is the C-ox, which we care about a lot in the past for scaling. But there are other capacitance. These are the so-called parasitic capacitor. You will have capacitor to other places. Nowadays, C-ox is no longer dominating. When you are trying to charge the gates of a device, you not only need to charge the C-ox, you also need to charge this parasitic. Okay? So now the delay time is actually proportional to C ox plus C parasitic. And because of this, if you keep scaling C ox, it doesn't help much. You want to do something to reduce the parasitic. So that's why we don't reduce as much. And the gate length, right, which is proportional to gate length. And that's why what we are really scaling today is not C ox nowadays. It is something called the contactor poly pitch, which we call CPP. Here you call it CGP, but we call it CPP also. Okay. So this is another view, right? This is the node, right? You go from 10 micron technology all the way to 10 nanometer. You see that historically, the node number equals to the gate length. Because at that time, that is what important. And later, we are too good, right? The engineer, right? Or the Intel TSMC, they scale the gate length even more than what Dennard asked for. Oh, so that's a boom. But after that, nowadays, after 22 nanometer, your gate length is larger than your node. So when people, nowadays people, TSMC say that 5 nanometer is in production, it doesn't mean that the gate length is 5. It's about 10 to 12. Okay, so it's, but that is no longer important. And what we care about is the, have some glitch here, yeah. It's actually the so-called CPP, okay? Now, since time's up, I won't continue. I will do it next time. And if you have any question, please let me know.